Good afternoon and welcome to today's webcast, Behind the Design, Compact Power Cable, presented and sponsored by Marmon Utility, LLC. My name is Jim Ducart and I am the executive producer of the T&D How video series. So in addition to this webinar, we also invite you to take a look at our T&D How videos on the T&D World website. Now before we begin, let me explain how you can participate in today's presentation. First, if at any time you are having audio difficulties or slides are not advancing, simply hit your F5 key to refresh your webcast console. If you have any technical difficulties during today's session, please press the Help button on your player console to receive assistance in solving common issues. This webinar technology allows you to resize the presentation by clicking the maximize icon or by dragging the lower right corner to enlarge the window. We welcome your questions during today's event. In order to submit your questions, simply type your question into the question window on the left-hand side of your screen and then hit the Submit button. We'll be answering as many questions as possible during the Q&A session that will follow the main presentation. But please feel free to send in your questions at any time and we'll add them to the queue. Please also be aware that today's session is being recorded and will be available within the next day for you to review. You'll be notified by email when the archive is available. With that, I want to introduce Adam Filion, who is the Chief Engineer for Medium Voltages Cables with Marmon Utility, LLC. He is responsible for the product design and technical support on 5 to 46 kV medium voltage underground cable, including both TRX LPE and DR EPR insulated constructions. He is a member of the ICEA, IEEE, and CSA. He has been a part of the wire and cable industry for over 11 years, all of which has been in a product engineering capacity. Prior to joining Marmon Utility, Adam spent over 10 years with General Cable, where he had been part of their product engineering group, serving in various roles at multiple locations. His latest role there was as an advanced engineer for electronics cables. He has been involved with various cable types and designs, including industrial and specialty, flexible cord, electronics, and now medium voltage power cables. Adam graduated from the University of New Hampshire with a bachelor's degree in mechanical engineering. Now over to our presenter. Adam, the floor is yours.
Thank you, Jim, and good afternoon, everyone. I'd just like to take a moment and thank you for joining me here today as we talk about PILC cable replacement design, reduced diameter cables. With that, second here. I'm having just a slight difficulty here with the presentation. It doesn't want to change slide, but I don't know if, again, sorry, this I'm not sure if anybody can see the slides, but it's, just a second here. Just trying to get the presentation up corrected here. No, don't worry about that. Bear with me one moment. All right, here we go. Sorry about that. Not sure what happened, but we're ready to go again. So, that's not what we want there. All right. So first planned stop, the agenda. What are we going to talk about here today? Well, I'd like to start with talking a little bit about the PILC cable. Get a brief overview of what it is, where it started, some of the basic design elements within that, and then talk about replacing it. What are some of the key challenges that we're going to face when looking at replacing it, and then what are some of the reasons why we want to replace it. And then I want to get into the solution of some of those challenges in the replacement design, the reduced diameter solid dielectric power cable. I want to look at things to consider when choosing a design, talk about some of the benefits that you can achieve through a reduced diameter design. And then we're going to get into the KeyRight solution. After that, we'll end it all with a little summary and recap of what we talked here today. And open up questions after that. So, first off, PILC cable, what is it? Well, literally, paper insulated lead cover cable. The design dates back to the early 1900s, where it was a solution at that time to a growing demand for power generation. It was installed in underground power systems, primarily in up-and-coming cities where large population. And it proved over the years to be a very reliable cable, and it's still in use in many of today's power systems. So looking at the basic design components, there's something to note up front here. There's a variation of designs that you might find with paper and PILC cables. For this presentation, for today, I'd like to focus on 3-conductor cable medium voltage designs. So when I reference PILC cables, that's what I'm going to be referring to. So with that, let's take a look at component number 1, the conductor. So a key element to the PILC cable was the choice of conductor. A lot of the designs utilize a compact sector conductor. This is a stranded conductor, and it's stranded in a way where you're able to really shape and form the conductor to achieve a very small cable core diameter. So the 3 conductors would be formed kind of like pie-shaped wedges, put together, and to achieve a very low-profile cable. Again, other options where you may find other options being used, such as compact round conductors, but the compact sector conductor was the key for a low profile. Going on to the conductor shield, they utilize semiconducting carbon black tapes. Continuing on here, the insulation, as the name indicates, paper insulation or paper strips wrapped around the conductor. These paper strips, were unique paper designed for the cable insulation. They were cut to specific thicknesses and widths, depending on what cable voltage you were looking at. And in turn, they were then impregnated with oil once wrapped around the conductor for the dielectric. From there, we'll move on to the insulation shield. Similar to the conductor shield, it was a semiconducting carbon black paper tape. Then for metallic shield, you'd be looking at copper tapes generally for PILC cables. Then over the cable core assembly, you'd have an extruded lead sheath. And over that, you could have an extruded overall jacket. Now, a note here is that some of the earlier designs may not have used the overall jacket. You could have been deployed with just the lead sheath. But over time, it was learned that having a protective overall jacket really helped extend the life of the cable, and so became more utilized. And just another note here on the basic design elements. The original PILC cables were typically targeted at 60C constructions. But over time, as technologies increased and materials got better, the operating temp for PILC cables made it up to 90C. So let's move on to a little bit of the benefits from the PILC cable. One of the key things here is its low profile. PILC cable design allows for smaller diameters thanks to its compact sector conductor. That was one of the key components of this low profile. The lead sheath, it was a very great barrier layer in terms of moisture resistance. Reliability. These cables proved to be very reliable. You had some installations dating back to over 80-plus years. So from a performance perspective, looking back at these cables, they're well-designed cables that did their job. So if that's the case, then why do we want to replace them? Well, there's two concepts that come into play, really. You have the physical cable that is going to be removed and replaced, but at the same time, we're also replacing the design. And so the replacing the design piece comes in due to the lead. And you see on here, there's a quote from an article I found back in 2003. For at least the last 10 years, the EPA has been asking utilities to get PILC cable out of the ground. Well, at this point, it's about over 25 years now. But the EPA has, come out with strong environmental concerns in terms of lead and its interaction with our water. OSHA is another driver of the design change with health concerns and as it relates to employees working with lead and the extra training and medical surveillance needed for that. And then you get into, the replacing of the physical cable and what are some of the reasons why we need to place the cable itself, not just the design, and that's cable deterioration. It was a great cable design, but nothing's perfect. So over time, you could have fatigue cracks in the lead, and this could be due just, normal wear and tear. So many thermal cycles, cable expands and contracts, and maybe the cable's been pushed a little bit over its limits, and just over time you end up with a crack in the lead. That's going to open a pathway for any moisture, and once the moisture gets into it, the insulation, you're gonna have a cable failure. In addition, with the oil impregnated into the paper, you could have draining or migrating with PILC cables that are either vertical risers or on slopes over time. So looking at that, there's also specialized workmanship. Working with the lead, there was a specialized set of skills that we don't commonly see anymore today. Like the design, there's been a shift in skill set as we've gone to extruded solid dielectric cables. And in turn, there's been a reduction in PILC cable suppliers. Harder to come by, again, with the change in design, change in manufacturing techniques and technologies. Now, if you look at the graphic on the right, it's just a good demonstration of what that specialized workmanship could entail. You have the worker on the surface there who has to heat the lead and bring it to a molten state, at which point he can lower it down into a manhole, into the vault, where the workers down there can take that molten lead, apply it to the cable joint with splicing, PILC cable. So it can take some training and a lot of work working hands-on with the lead. So there's a great video on YouTube and showing lead wiping, an example of lead wiping with PILC cable. And so the next couple of slides are just some pictures from that. You can see that the worker here has a ladle with some molten lead in it. As he pours it onto the cable joint, he's kind of holding the molten lead there in place and letting it start to cool and solidify. And as it's doing that, he starts forming it. You can see as, you can then start to shape it as, again, it cools and solidifies until you get to the final product there. So just a good video to check out if you can on YouTube. So, that brings us, to the to the replacement solution. The reduced diameter power cable. So one of the things to keep in mind when you go to replace PILC cable, you want to replace it. The goal is to replace the cable without replacing the entire duct system, right? That's why we're looking to reduce the diameter so it can fit into the existing duct, as opposed to tearing up the city, and having to replace an entire duct system. Be a lot less, a lot more cost effective if you can just replace the cable. But when you're replacing the cable, you don't want to just replace the cable, but you want to make sure it's at least as good as what was there, but realistically, you want it to be better performance, right? That power system's existed there with PILC cable for some time, and the demand has changed since the original installation. So what are some things to consider when replacing PILC cable? Number one, the installation conditions. Take a look at that existing duct. Look at the size of it, the condition of the duct. Not only are you going to be able to install a cable in that duct, but are you even going to be able to get the PILC cable out of it? And when you do, what's left behind? You've got to look at those conditions pretty carefully. Shield fault current capability. Again, you need to be matching what was in there or better. Flexibility of the cables, another key component. Again, being installed into existing duct, flexibility can become very important. Ampacity of the cable, like shield fault current capability, you're looking to match what was there, if not do better. But with each replacement opportunity, it really needs to be evaluated on its own, and custom designs may be required. You won't have one particular cable that can one-size-fits-all type of deal when replacing PILC cable. There's going to be a lot of design trade-offs that need to be evaluated and looking at each situation. So let's take a look at the reduced diameter power cable layer by layer and see what options exist. So for each layer, I kind of put a brief description of the function of that layer, because you always want to keep that in mind and make sure what you're doing when trying to reduce diameter isn't compromising that main function. So first up, the conductor. Conductor transport the electrical current from one point to another. So what are some things to consider? Well, first up, the material of the conductor. Typical choice of today's world is copper versus aluminum. But if the goal is, you want the most current carrying capability and the least amount of diameter, copper's really the only choice there. So now that we've got copper conductor, we'll look at the design of this conductor. Typical choices are either stranded versus solid. But solid's not, although a smaller diameter, it's not very practical, especially when you get into larger casing mill sizes. It's not readily available, nor would you want to be very, very stiff. So you get a bonus with flexibility with the stranded conductor, as well as readily available sizes common to today's industry. So now we have copper stranded conductor. Typical choices, either compact versus compressed. With compressed conductors, you're allowed up to 3% reduction in diameter when compared to the round construction. Compact, you can go up to as much as 10% reduction in diameter. So when you're looking to reduce the diameter of your cable, compact's the way to go. A trade-off is that compact conductor will lose some of the flexibility granted from the stranding, but the gains in diameter reduction is just too good to pass up there. So if the compact sector conductors were great for PILC cable, why can't we use them with today's solution? And really, the compact sector conductor just isn't that conducive to today's manufacturing techniques. It's difficult to extrude a compact sector conductor. Now, that's not to say it can't be done. I believe it might be done over in Europe, and you may be able to find it still here in the States today, but it's more difficult. It's going to be more of an expense and very labor intensive. And so you typically won't see that. Moving on to the conductor shield. Conductor shield is to distribute the electrical stress at the conductor to avoid points of high stress. All right, so with that in mind, what can you do when it comes to reducing the thickness of the conductor shield? Well, right off the bat, if you've chosen compact conductor for your conductor, today's standards do allow a reduction in thickness with the compact conductor. You have you have a compact conductor with less interstice fill or air gaps at the reduced chances of any fall in from the conductor shield. You have a smoother surface on the conductor, and you'd be able to get away with a little less wall thickness there. Now, you could look to further reduce the wall thickness, based on performance, but that needs to be evaluated in each situation. There are some performance-based standards out there today that do take a look at this, and again, I think they allow you to go down, I think down to 5 mils in some cases, which is pretty much just telling you that there needs to be something there. But you got to do that and exercise extreme caution when reducing that thickness that far. Not only do you have to think of the electrical performance, but this cable is going to be installed, it's going to be bent, it's going to be in cold temperatures, hot temperatures, and that physical abuse could cause some damage to a thin conductor shield. And any damage to the conductor shield is going to introduce really high points of stress that are going to cause cable failure. So something to always keep in mind when evaluating reducing diameter. On to the insulation. So insulation to prevent current from coming into contact with other conductors. In addition, it also prevents current from coming into contact with any supporting hardware or people. It's a very important aspect of the cable. So looking at the insulation, look at material selection. Typical choices today's world are ethylene propylene rubber or tree retardant cross-linked polyethylene. So some things to consider when trying to make that choice. What's the cable going to be exposed to? It's in an underground duct system that's been there for X amount of years. Don't exactly know the entire condition of it, but things to consider are resistance to water, flexibility of the cable, as well as the temperature rating. You're looking for a 90C, maybe a 105C cable solution. So once you have your material figured out, you can look at, is there an opportunity to reduce the wall thickness with the insulation? There may be some opportunity, but this really should be kept as a last resort. There's some performance-based standards that will allow you to look at the overall design and, instead of coming up with a wall thickness based on a voltage class, come up with a wall thickness based on the dielectric strength of the material and designing a higher stress cable. But again, with cables today, trying to get the most out of them, chances are that cable's going to see, maybe a higher loads than it's intended for at times. Any additional insulation you keep on the cable, you want to do just that. Insulation shield. All right, to confine the electrical field and provide uniform radial electrical stress within the insulation. Kind of, make an electrical field sandwich with the conductor shield. The insulation stress control layer. So, wall thickness reduction is applicable with the insulation stress control layer, similar to the conductor shield. In this case, when you go to apply the metallic shield, you could reap some benefits from using shields such as flat strap neutrals or copper tape, shields that don't apply any neutral indent. Today's standards, they take into account a certain indent with the round concentric neutrals or standard URD. If you remove the flat strap neutral or copper tape, you're significantly reducing any indent into the insulation shield, therefore allows you to reduce some of that wall thickness. Similar to the conductor shield, you can look at performance-based reduction and take it a next step further. But again, the same cautions as with the conductor shield applied for the insulation shield. You want to really take a look at how that cable is going to be installed, what it's going to encounter in terms of physical abuse, and is that thinner insulation shield going to hold up. Moving on to the metallic shield, the ground insulation shield surface and provide a path to ground for charging currents. In addition, to provide a path for fault currents and provide a system neutral. So diameter reduction, I'm going to talk about in two respects. One as a direct result of the type of shield you chose, and one as an indirect result of the type of shield you choose. Now, what I mean by that, looking at what I'm calling a direct result, looking at things like I just mentioned, copper tape and flat strap neutrals, where when compared to the round concentric neutrals of the standard URD cable, the actual metallic shield thickness is decreased. When it comes to copper tape, most copper tapes, around 5 mils thick, maybe a little thicker, 8-10 mils. Flat straps, what you're essentially doing is taking the round concentric wire and reshaping it. You're modifying it so that you're reducing the thickness of it. You're not changing the circular mill area, you're just changing the shape of it. And onto the indirect results, or what I call the indirect results, diameter reduction. You have the insulation shield thickness reduction that we just talked about. With minimizing the neutral indent, you're allowed to then reduce the insulation shield. So you could have a twofold event there. A little more on the flat strap design. Flat strap neutrals are very versatile. The thickness can vary to meet whatever, to try and meet the requirements that you need. And to help depict that, and look at the reduce the graphic in front of you, where you have a 14 gauge round concentric neutral, and to the side of that you have a couple different options. If you were to take that 14 gauge neutral and try to create a flat strap to fit a particular design, again, really all it comes down to is what tooling do you have to make a flat strap. You can see as the thickness reduced, the width does increase. So you do have some concerns about coverage over the insulation shield. So something to consider. Again, another design trade-off that needs to be thought about. When looking at the shape of the flap strap, there is certain requirements that you do need to meet. One, minimum thickness of 19 mils, and then you have a minimum width requirement as well. Again, you don't want these flat straps getting so thin that they, are breaking as the cable bends or is installed. Moving on to the jacket. So the jacket's there really to protect the core of the cable from physical abuse, chemical and water attacks. It's there to also protect the metallic shield from corrosion. Now, jacket does serve some other functions such as sunlight resistance and flame resistance and so on, but for today's purposes, no, I'm not really considering those, although you may need to if the situation comes up. So, what to consider in terms of jacket? Well, again, you want to look at what the cable is going to be exposed to. When it's undergoing installation and while it's in operation. how much physical protection does the cable need? You can also look at material options. You want something with probably more abrasion resistance than a standard linear low density polyethylene of standard URD cables. Polypropylene and high density polyethylene are two good options in that regard. And then when it comes to reducing the wall thickness of the jacket, again, it's a trade-off that needs to be reviewed, evaluated. Do you need a lot of jacket protection? Is it going into a duct that's been damaged over the years, or maybe it's going into a duct that's very clean and no issues with it, and where you can feel comfortable about reducing the jacket thickness and getting away with a little less protection. Again, you've got to look at each situation and evaluate it. Now, we just went through layer by layer of the cable and talked about possible options you have to reduce the diameter of the cable, but that's not necessarily the order you want to go when you look to actually come up with a design. What you want to do when reducing the overall cable diameter is start with the conductor. From the conductor, you want to then look to the metallic shield. After metallic shield, you look into the jacket thickness. From there, then you can get into looking at reducing the wall thickness of the conductor and insulation shield thicknesses. Again, there's a few options there. And then again, in last resort is the insulation thickness. If you can get away, with the standard wall thickness for the insulation, still meets the requirements you have, that's great. That's what you want. Something else too you can evaluate is the possibility of reducing the duct clearance. You have your existing duct. There's ways to determine the duct clearance that you have available, and are you at a ½ inch clearance? If not, can you take it down to there? Perhaps you can even reduce the clearance beyond a ½ inch if you're looking at a very clean, a very good duct, existing duct, and so looking at duct clearance, you might even do before looking at the insulation thickness. And as I mentioned earlier, there could be a lot of variation in designs. It may not be one particular solution that does a job. You may be able to get it done in one or two or three, but there are design alternatives. You could be looking at a single conductor cable, or you could be looking at a 3-conductor cable with 3 shielded conductors assembled together under one single overall jacket, versus 3 single conductors triplex together. Again, something to be evaluated for each situation. And that brings us to Marmon Utilities' KeyRight solution. So what do we do here? So looking at the conductor, compact copper, no-brainer right there, done. Then onto the conductor shield. Well, KeyRight has a unique conductor shield, and it's PermaShield, which we'll get into a little more after this. And then along with the PermaShield is another unique component found only in KeyRight's cable is KeyRight's discharge-resistant ethylene propylene rubber insulation. Use an extruded semiconducting layer for the insulation shield. Go with the flat strap neutral design. We have polypropylene jacket, a single conductor construction as opposed to a 3-conductor cable under a single jacket. There's with a single conductor construction, you're looking at longer possible lengths than a 3-conductor cable, as it's what you can fit on a single reel. Longer lengths mean less splices. Polypropylene jacket, again, it's more abrasion resistant than linear low density polyethylene, and we find that it's a little easier to work with than high density polyethylene. And another aspect of the single conductor cable, the KeyRight Cable Service Group, they have a lot of installations under their belt, been in the industry for a long time, and dealt with a lot of contractors and whatnot. And it's been their experience that, when it comes to splicing and terminating, a single conductor cable is easier than the 3-conductor cable. So, PermaShield. All right, as I said, this is unique to KeyRight cable. It was invented by KeyRight back in 1958. It's a non-conducting conductor stress control layer, and it's recognized as such by AIC and ICEA, rather. And the goal of PermaShield is there to reduce the electrical stress at the interface of the insulation interface, and overall lowers the maximum stress level. Now, because it's non-conducting, another bonus of PermaShield is that you can test it 100% in production. It undergoes a 2,000 volt DC spark test, which can't be done with your conventional semicon. So the key characteristics of PermaShield is low conductivity, moderate dielectric strength, and a high dielectric constant. And as a conventional semiconducting shield will transfer the electrical stress directly to the insulation interface, the PermaShield, due to its dielectric strength and dielectric constant, will actually reduce that electrical stress as it's transferred to the insulation, therefore reducing the electrical stress at the insulation, the peak electrical stress, I should say, which you can see here on this chart, and therefore reducing the average stress across the insulation as a whole. And that's a key component when talking about reduced insulation wall thickness for a KeyRight solution later on. That brings us to the KeyRight insulation, discharge-resistant ethylene propylene rubber. It's a proprietary compound, formulated, mixed, and extruded in-house. It's got a great history of 40 years of successful field history, not just in medium voltage cable, but also applications up through 138 kV. As its name describes, it's formulated to resist partial discharge and recognized as such by AIC and ICEA. Now, the PermaShield and insulation system together has a proven track record over a number of years. Even prior to today's standards, such as ICEA, that dictate the wall thicknesses per voltage class, this system was used regularly at what we would consider reduced walls of today in the past. As these standards became adopted, this insulation system, KeyRight actually had to increase the walls to conform to the standard. So not only does it have a great track record in the field, but it also has experience, a good track record of reduced wall construction from the past. Here is the discharge resistance test required by ICEA for the discharge resistant design. Again, it's discharge resistant, therefore it's not subject to the same partial discharge testing for discharge free designs. Instead, once a month, the compound undergoes this test as described by ASTM, where you have a compound plaque between a probe and ground, and you apply a high voltage, 21,000 volts AC, to the sample for a given amount of time. And then you look at those samples for any degradation. And here's just results of comparison tests between the standard discharge-free design materials and the discharge-resistant when undergoing that discharge-resistant test. And as you can see, the discharge-resistant EPR on the bottom left shows no signs of degradation, where the other samples show high signs of degradation. And that's, again, discharge-resistant EPR. That's the KeyRight cable right there. So, benefits of the reduced diameter power cable. You know, primarily, it's less expensive alternative than replacing the entire duct system. You know, there's no lead sheath. You know, just put smiles on the EPA's face. No oil used in the cable. You don't need to worry about oil migration or draining on slopes and risers. It's in line with today's standard manufacturing installation practices. You're not monitoring for lead in blood of workers. It doesn't require lead wiping skills. And one thing to note also, you have an increase in emergency and short circuit temperature ratings. PILC cable, you typically would have up to 110 degrees C and 200 degrees C for emergency and short circuit temp rating, again, due to the lead. And then with today's reduced diameter power cables, you're looking at the standard, 130 and 250 or 140 and 250 degrees C emergency and short circuit temperature ratings. Some other benefits, the accessories today that are readily available are suited for these solid dielectric extruded cables. So those are more readily available for these cables. The design is customizable. Again, you can look at each situation on its own, and you have various options of what to look for, with different ways to reduce diameter. The cables are typically lighter, easier pulls than your PILC cable. Looking at increased flexibility, and when looking at the single conductor option, you have longer possible lengths. All right, so this is just a quick design comparison between three cables, and it's very important to note that the only scale here is in reference to the overall diameter. And the individual components and cables aren't necessary to scale. That's my limited skills right there, but the overall diameter is what to look at. Again, I started with a commercially available PILC cable, looking at 500 kc mil, 15 kV with 100% insulation level. Then I went to a standard URD cable of similar size, and then from there I tried to reduce that cable with the options that we talked about earlier, looking at the conductor, the jacket, the metallic shield, and then even the reduction in the walls with the conductor and insulation shield and insulation. But, again, it's just to get an idea. It's for example purposes only, not knowing the exact, shield fault requirement of the PILC cable. That could alter this design, so don't take these numbers to heart. It's just, get an idea of what can be done. So, to summarize what we did here today, PILC cables, they were great designs with an outstanding track record. But, with EPA and OSHA and, concerns raised with working with lead in general, both manufacturing of and, installing PILC cables, there's really been promoting a change in design. And with that came the reduced diameter power cable design. Again, we looked at design parameters and considerations to review various options, wanted to look at variations in design, and really getting custom designs for specific installations. From there, we took a quick look at the KeyRight solution for PILC cable replacement. Again, that's the preferred solution, not necessarily limited to just that, but every situation, can be reviewed and evaluated and, come up with hopefully a reduced diameter cable that saves you from replacing the entire duct system. And so that's it for the presentation, and we'll open it up to questions.
Yeah, thank you, Adam. That was a terrific presentation. This is Jim Ducart again. A few of you have already submitted some questions, so we're going to jump right in with some of them. While our presenters are answering, while Adam answers questions, if you could please take a moment to complete the feedback form that appears on the bottom of your screen, we would greatly appreciate it. Now, the first question is, Adam, can you talk a little bit about the benefits between PP and LLDPE jacket?
So between polypropylene and the linear low density polyethylene. So when it comes to PILC replacement, the polypropylene jacket is really more abrasion resistant. Right? It's going to take a little more abuse without tearing than the standard linear low density polyethylene. And so therefore, when you're looking to reduce the diameter of the cable, but you don't really necessarily want to compromise protecting the cable core, protecting the shield. Polypropylene would hold up a little better than the linear low density polyethylene.
Excellent. Okay, another question, one that I had, and we also got sent in, is which insulation is more used today, EPR or TRXLPE?
Well, I believe they're both used, and I don't know exactly what is used more. From my experience, I've seen the ethylene propylene rubber being requested more than tree retardant cross-linked polyethylene. But again, that's something I can try to gather a little more info on, as I don't know what's actually being used more.
Okay. Got a question. How does the jacket water permeability compare to PILC?
I'm sorry, can you repeat that?
Yeah, it says how does, I assume they're talking about the KeyRight solution. How does your jacket water permeability compare to PILC, paper insulated?
So when it comes to, water resistance and stuff, the jacket's an extruded to fill jacket. So it's filling the interstices of any of the flat strap neutrals, the gaps in between. But the water resistance really comes from the insulation. It's water resistant insulation. It's that's the key component with the KeyRight cable.
Okay. Here's an interesting question. Is lead cable really all that bad? Your thoughts on that?
Well, it's you have to look at, depends on the perspective, right? From a cable design perspective, it turned out to be a great design. You have cables that are still functioning today over 80 plus years of installation. But when you're looking at maybe health and the environment, there's been a lot of research, a lot of work done that shows lead getting into our water systems and lead getting into our blood, being very harmful. So it's all about perspective, but I think the industry has taken the perspective more leaning towards the EPA and the OSHA and looking to remove lead where possible.
Excellent. What is the predicted lifespan of reduced diameter TRXLPE cables?
Well, I don't deal with TRXLPE that much, but
okay.
In terms of the KeyRight EPR solution, it's got the same life expectancy as the standard cable. Again, that's something you want to consider when evaluating the situation, because the goal is to maintain that life expectancy when you're looking at evaluating the design. You're looking at 40, 50, 60 plus years in that regard.
Now, you may have answered this in the presentation. Got a question, is PILC replacement cable new? Is what you're talking about new, and or how long has it been around?
So it's PILC cable's not new. It's been, I think I had a slide in there with a quote, from 2003 saying it's been requested for about 10 years. So we're looking, over 20 years, 25 plus years, that there's been that change in mentality when it comes to lead. But some of the PILC cables, there's still a lot being used in today's power system. So although it's not new, it's still very relevant.
Okay, fair enough. What would you consider the most critical aspect of the replacement cable design? I know you listed a few of them. What sort of, I think you even listed them at one point in order, but go through that again. What are the most critical aspects?
Well, typically with PILC replacement, you're looking to take a cable out and replace a new cable in the existing duct system. So, diameter kind of determines all that. So diameter is probably the most critical piece, and from there you can start looking at each layer and seeing how you can fit the diameter, where the conductor would probably be the first spot to look, and insulation being the last place to look to reduce diameter.
Well, and in fact, that leads right into the next question, which is looking at diameter only. Is there a particular design that can achieve the smallest overall diameter?
So when looking at designs and just trying to get the smallest diameter possible, your best bet is probably to go with a three-conductor cable, three conductors, cabled together under one overall jacket. But that depending on the shield fault requirement and whatnot of the situation, or manufacturing capabilities. Again, you get into all the other design trade-offs as well. It may not be the best choice, but in terms of diameter only, that's probably what you're looking at to get the smallest overall diameter.
And then staying on diameter, somebody asked, when you have a larger diameter and a greater fill of your duct, how do you not reduce cable capacity with limited heat dissipation?
That's the question I don't know off the top of my head. That's something I might have to look into a little bit,
okay,
and get back to that person.
Had a question. How is the cable rating being impacted compared to a similar oil-filled cable?
It's in terms of cable rating. You're looking really to get a equal cable. With the PILC, whatever is rated, you look at the voltage rating of the cable, or the shield fault current capability of the cable, the temperature rating. You're really looking to get an equivalent cable in there, or better. I mean, a lot of those systems, again, I've been there for a while, and over time the power demand has changed. So getting an equivalent may not be enough, where you actually want to get better performance. So again, looking at cable ratings, voltage, temperature, shield fault current, conductor ampacity, all that, you're looking to at least get equivalent to the PILC cable.
Excellent. We got a lot of good questions coming in here. I want to make sure I get to this one. Somebody's asking you to discuss cable lugs, selecting and sizing lugs for compact conductors.
Well, so I don't have too much experience with that. I don't think I'm going to be able to get an answer right now, but I do know the group of people to talk to that do have experience with that, and I think together we'll be able to get an answer and get back to that person.
And then another question, are there bend radius concerns or restrictions to be aware of with these new cables?
So in terms of bend radius, again, I think standard bend radius may apply, but if you're starting to look at, getting very thin walls on some of the conductor shields, insulation shields, and whatnot, you want to be aware of that bend radius again. if you go too thin, you don't want to. You're not looking to damage those elements when bending and installing the cable. But typically standard bend radius. Radius applied.
And what about the friction factor of reduced diameter EPR compared to PILC cables?
Well, you'd be looking at the polypropylene jacket, and there's another component I think I touched on a little bit. You have a much lighter cable with the replacement design. So PILC cables, you may have a PVC or polyethylene jacket, and so with the replacement cable, you have a polypropylene jacket. I don't know exactly, but I'm assuming relatively similar when it comes to friction with linear low density polyethylene, but you have a lot less weight, which will certainly help when it comes to friction and cable pulling, making the pull easier.
Well, I'm afraid that we've run out of time. I'd like to thank our speaker, Adam Filion, for his outstanding presentation, and also thank our sponsor, Marmon Utility. Thank you, and have a productive remainder of the day.